Hey, welcome back. Today we're talking about something, well, something you're using right this second, but I bet you never really think about it. The fact that, in a very real way, the entire internet is made of light. Yeah, pure light. So let's get into it.
I mean, really think about it for a second. How is it possible that you can click on a video from, say, Japan, and it just appears on your screen in milliseconds? It feels like actual magic, right? But it's not. The secret behind this incredible speed, well, it's just some really, really cool physics. And the answer, the physical thing that makes it all work, is this massive, global network of tiny glass threads. We're talking thinner than a human hair, and they're carrying all our data as little flashes of laser light. We call them optical fibers, and they are literally the backbone of our entire digital world. Okay, so we're talking about trapping a sunbeam, or, a laser beam. How in the world do you get a beam of light to travel down a tiny glass thread for thousands of kilometers? And not just in a straight line, but around corners. Well, it all comes down to this one brilliant little trick of physics, a phenomenon that lets you trap light perfectly. So, to get this trick, we need one quick concept. It's called the refractive index. Sounds complicated, but it's not. Basically, it's just a measure of how fast light can travel through something. See, light is fastest in a vacuum, but the second it hits something like water or glass, it slows down. The refractive index just tells you how much it slows down. You've seen this. You know how a straw in a glass of water looks like it's bent at the surface? Yeah, that's the refractive index in action. All right, so here's the magic trick itself. It's called total internal reflection, and the idea is just beautiful. It's so simple. First, you have light traveling inside a dense material, like our glass core. Then it hits the edge, the boundary, with a less dense material, but it hits it at a really shallow angle. And when that happens, it can't get out. It reflects perfectly, perfectly, like a mirror with zero loss. It just keeps bouncing and bouncing, completely trapped inside. And this right here is the absolute key to the whole thing. The core of the fiber must have a higher refractive index than the material around it, which we call the cladding. That's it. That's the secret sauce. By making the core just a little bit slower for light than the cladding, you create that perfect light trap. The light just bounces down the core forever and takes all our data along for the ride. Okay, so we've got the principle down. We figured out how to build the perfect light pipe. But how do you go from a cool physics principle to a real product? How do you make the millions and millions of kilometers of cable that connects the entire planet? Let's take a look at what a modern optical fiber actually looks like. Okay, get ready for this because the scale is it's mind-boggling. Look at this breakdown. The core, the part that's actually carrying all the light, all the data, is only 8 micrometers wide. To put that in perspective, that is smaller than a single human red blood cell. It's insane. Everything else you see here, the cladding, the buffer, the jacket, that's all just protection for that impossibly tiny, incredibly precious core. And you can see right away why this was such a massive leap forward from the old copper cables. With optical fiber, the light signals lose way less energy over long distances. Plus, and this is a big one, since it's light and not electricity, it's totally immune to electromagnetic interference. From power lines, big motors, all that stuff that can mess up a copper signal, fiber doesn't care. It's a clean, pure signal. Now, it's easy to take this for granted, but this didn't happen overnight. There was a huge challenge that basically unlocked the entire internet age. For decades, fiber optics was kind of just a cool lab curiosity. The problem was, early fibers lost so much light that the signal would basically disappear after just a few feet. So to build a global network, scientists had to solve this one massive problem. They had to figure out how to make glass that was purer than anything anyone had ever made before. And this journey to practical fiber, wow, it took a long time. Look at this. The basic principle was first shown off way back in the 1840s. The name fiber optics didn't even exist until 1960. But the real game changer, the idea that kicked everything into high gear, came in 1965 from a scientist named Charles K. Kao. So here was his brilliant insight. See, everyone at the time thought glass itself was the problem, that it just wasn't good at letting light pass through. But Kao said, no, you're wrong. He proposed that the issue wasn't the glass, it was tiny little impurities inside it. And he theorized that if you could somehow remove those impurities and make perfectly pure glass, you could send a signal for miles. This idea, it completely changed the game. And yep, it won him a Nobel Prize. And this chart shows you how right he was. Look at the signal loss, or attenuation, in those pre-1970s fibers. It was terrible. But after Cal laid down the challenge, researchers at a company called Corning got to work, and in 1970 they made a breakthrough. And then look at modern fiber. The improvement is just staggering. We're talking about a 100-fold drop in signal loss.
So what does that number, 0.2 decibels per kilometer, actually mean in the real world? It means this: if you shoot a pulse of light down 10 kilometers of modern fiber, that's over 6 miles, an incredible 71% of the original light energy makes it out the other side. Think about that. That's how insanely transparent this glass is. And that is what makes our global internet possible. But here's the cool thing. This amazing technology isn't just about the internet, not by a long shot. The same principles that let us stream videos from across the globe are being used in all sorts of surprising ways, in fields you would probably never guess. And this table really just lays it all out. When you compare optical fiber to the old copper cables, it's no contest. Bandwidth? Way higher. Distance? It can go over 100 kilometers before you even need to boost the signal. It's immune to interference. It's way harder to tap into, so it's more secure. And here's a funny one. Nobody wants to steal it because it has no scrap value. Can't say that for copper.
I mean, the versatility of this stuff is just awesome. You've got medical scopes that let doctors see inside your body. You have sensors that can measure the insane temperatures inside a jet engine, or tell if a bridge is under too much stress. The military uses it for jam-proof drones. And yeah, of course, you've definitely seen them in those cool decorative lamps and toys.
So when you step back and look at it, it's really incredible. This whole thing started as a simple physics trick, basically a parlor trick of guiding light through a stream of water. And from that, it has evolved into the central nervous system for the entire planet, a global network that's all powered by nothing more than trapped light. You know, light gave us this completely connected planet. It just makes you wonder, what's it going to illuminate for us next?